In this lesson, we'll be looking at a subset of the general reaction types that we discussed in the last lesson, redox reactions. The unique feature of redox reactions is that electrons are transferred between reactants, which causes the oxidation numbers to change. By the end of this lesson, you'll be able to identify which reactant is being oxidized and which is being reduced. So first, just kind of a quick overview of the different reaction types. So if you are combining simple things together to make a more complex thing, it is a synthesis or combination reaction. If you're taking them apart, decomposition. If you have a single uncombined element and a compound, and then afterwards you have a new compound and a new single uncombined element, it is a single replacement reaction. Remember, with that one, in order to figure out whether the reaction is actually going to take place, we have to consult the activity series. And then we have the two compounds going to form two new compounds. That was a double replacement reaction. And then this is where we have to look at the solubility rules to determine if that reaction is going to occur or not. Not all reactions occur just because you write them down on a piece of paper. And then the fifth main category would be a combustion reaction, which is where you have a hydrocarbon and oxygen. Oxygen is always present in a combustion reaction. And afterwards, you have carbon dioxide and water. All right, so redox reactions are ones in which the reactant's oxidation numbers change. And so we saw some of this when we were trying to write formulas for different compounds containing transition metals. So remember, there's an algebraic way we can do it, which is like for the first one, FeCl3, we can say, all right, well, we have X is going to be the iron. We have 3 chlorides. Each chloride is -1, adds up to 0. So this is iron with a +3 charge. The other way you can do it, and I need my pen, is you can say, all right, well, I got 3 chlorides. Each chloride is -1. So that means the total negative charge is -3. So that means iron is +3. Try to avoid doing reverse swap and drops, because if you have something like oxygen in there and not a halide, it's going to cause you trouble. So then we go through and do the rest of them. So SnCl2, which used to be called stannous chloride, is tin with a +2 charge. So now it's called tin 2 chloride. And then we have ferrous chloride, excuse me. See, there's a lot of memorization involved. I'm not so good at it anymore. And so we do the math, and we figure out this is iron to the +2. And then you do the next one, which is stannic chloride, and do the math, and we get that it is actually the new name, modern nomenclature would be tin 4, Roman numeral 4 chloride. All right, so when I was an undergraduate in college, I had a professor that used redox thermometers as a way to help us remember whether the reactant was being oxidized or reduced. His rationale was that we are used to the idea that if the temperature goes down, so if temperature goes down, that means it's being reduced. Works the same way with the oxidation number. If the oxidation number is becoming more negative, it is being reduced. And so we look at the iron, it's going from +3 to +2. So it's going down the redox thermometer. So the iron 3 is being reduced. And then we look at the other one, and we got tin going from +2 to +4, so it's going the other way. So it's being oxidized. And the oxidized part is actually kind of a historic term. It came from observations that, in my pen, if you went from something like elemental sulfur, which has an oxidation number of 0, and then if you went to SO2, now sulfur has a charge of +4, or maybe SO3, now we got a charge of +6 on that sulfur. We have more oxygens on it, its oxidation number is getting higher, so it is being oxidized. That's probably also where the term oxidation number comes from. All right, so let's look at some examples. So the first thing you have to remember is that, or just know, that elements are always going to be zero. And if you kind of look at the second example where we have copper metal, if you think about it, did you ever get zapped off of holding a penny? No, that's because it doesn't have a charge. So copper is going to be 0. And then we figure out the oxidation number of the tin. We just saw this one. That's tin plus 2. Now I see that I have chloride on the other side, so I'm going to do the chloride in this case as well. So we got -1 for each chloride. So if chlorine is part of a binary compound, it has an oxidation number of -1. And then we got tin with the +4, and then the chloride with the -1 again. And so part of what I want you to learn how to do is to learn how to identify the redox pairs. And so you just say, all right, well, I got chlorine is changing its oxidation number. So I'm just going to draw a line to connect that. And then the other one is tin is also changing its oxidation number. So then you think about your little redox thermometers, and you say, well, chlorine is going from 0 to -1, so it's going down. So that means chlorine is being reduced, and so therefore tin has to be oxidized. You can't have a reduction without an oxidation. If we got one, you got the other. And so actually, once you figure out one of them, like say, oh, I can tell that chlorine is being reduced, then I know automatically that the other one has to be oxidized. So let's look at the next one. So we have copper. I already said that that's going to be a 0. So this next one, we have silver nitrate. So silver is part of a compound. You can either remember that it is always going to have a charge of +1 when it's in a compound, or you can say, all right, well, I got a polyatomic ion. I'm going to draw a circle around it. That group has a charge of -1. So therefore, silver has to be +1. And I'm going to do the same thing over here with the copper nitrate. So I have 2 nitrates. Each nitrate is -1. So that means I have a total negative charge of -2. So now I'm back in the numbers I put into this PowerPoint. So we have silver is +1, copper is +2, and over here we have silver metal, so that means it's going to be a 0. So we're going to connect up the pairs. So copper is going from 0 to +2, so it is being oxidized. And then silver, therefore, has to be reduced. So something to keep in mind is that metals always form cations. So if you have a metal in a compound, an ionic compound, the oxidation number is always going to be positive. So if you see you have the elemental metal, and you see you have it on the in a compound on the other side, right away you know that that is the oxidation reaction. So let's go on to the next one. So group 1 metals are always +1. So, and they very rarely are involved in any kind of redox reactions because they're so reactive. So here we have potassium in a compound, potassium in another compound. It's not changing its oxidation number, so we're just going to ignore it. You see that we have chlorate present here. So chlorine is the central atom, and it has a whole bunch of oxygens attached to it, which means chlorine has been oxidized from its normal -1 state. So we do have to figure it out, and I already have the math shown down here. So we have +1 from the potassium, plus X for the chlorine. We have 3 oxygens. Each oxygen is -2. Whole thing adds up to 0. So this is chlorine with a +5 charge. The maximum oxidation number that the halogens below fluorine can have is +7. They can be anything from -1 to +7. Fluorine, because it's so reactive, so much more reactive than anything else, there isn't anything that can oxidize it past its -1 state. So fluorine is always going to be either 0 or -1. So then we have oxygen is the next one. Oxygen's in a compound, so it's going to be -2. Now we have chlorine as part of a binary compound, so it's back to its normal -1. And here we have oxygen gas. It's an element, so it's going to be 0. So we connect up our pairs. So ask yourself, we have chlorine going from +5 to -1. Is that an oxidation reaction or is that a reduction? Hopefully you said reduction, which means oxygen is being oxidized, which sounds kind of funny. So the reason why the redox reactions don't get included as part of the general 5 is because they are a subset of these other 5. And so we're just going to go through and identify what type of reaction each one is. And so here we have things being combined together to make one thing, so that's synthesis. And then the next one, we have a single capital letter on one side, and on the other side we have a new single capital letter, so that is going to be single replacement. And then here we have a compound being broken down into its parts, so we have decomposition. All right, so I got some practice problems from the worksheet that goes with this lesson. So I'm going to change back to my pen. And so this particular worksheet consists of writing formulas and then identifying redox pairs. So remember, silver is always going to be +1. And then oxide means it's oxygen with its -2. So we do the swap and drop, and you get Ag2O for the formula. Here we have titanium. It's got that Roman numeral after it, so it tells us immediately that it is +2. It doesn't mean that we have 2 titanium. It just tells you what the charge is. Oxide's -2. It's already charge balanced, so it's just going to be Ti as a dot O. All right, so for identifying the redox pairs, I just want you to connect the parts that are changing their oxidation number. So here we have gold 3 and gold metal. So that's one part. And then I want you to connect the other half. So we have lead 2 and lead 4. So that is also changing its oxidation number. So we're going from 3 to 0. So that means that this is the reduction. And that makes the other one the oxidation. When you're doing solving these problems, make sure you don't overlap these lines that are present. I've had people, they do this part right, and then they overwrite it on top of it, and I can't tell if they know the difference between the different reactants in the products, because you're supposed to be identifying the redox pairs in this activity. All right, so that's it for that one, and that's it for our lesson on this. So just to wrap it up, so redox reactions involve the transfer of electrons between the reactants, and that causes the oxidation number to change. If you have an oxidation, you're always going to have a reduction, and vice versa. That's because we're transferring electrons. You can't just lose some electrons from the one that's being oxidized and then not put them anywhere. They have to go somewhere. And this is as much because of the law of conservation of mass as anything else. And then oxidation number. Oxidation is the process when the oxidation number becomes more positive. So down here in the picture, I have our starting point, and then in this case it went, the top of the redox thermometer went up, so that tells us it's being oxidized. And then reduction, that's where the oxidation number becomes more negative. So again, we're comparing it to our starting point, and you can see that it's now lower, so it's gone down the redox thermometer, so it's been reduced. And then just remember, a lot of the other types of reactions that we've already studied are also redox reactions. The only one that is very rarely a redox reaction, and it's some really weird mercury chemistry is what causes it, is double replacement reactions. So we're going to say, in general, double replacement reactions are never going to also be redox reactions. All right, so that is it for redox reactions. Thanks for listening.